тройка правильно была указана.
Окей. Так, сейчас я должен все-таки тут выяснить вопрос с этими ссылками, потому что никто не сможет зайти. Сейчас, секундочку.
Хорошо.
Los enlaces. Estoy colocando ahora el chat de la sesión correcta. Pero quieren entrar a sesión 5 y les pide ese código, ya lo configuramos, ya no les debe pedir código. Por favor, entienden.
Entonces, en el sitio para la conferencia, donde usar las files, archivos, para actualizar y cuando las tarjetas.
Ya estoy por esto. De todas maneras, estoy conmigo.
Well, Iskander, meanwhile, you can start sharing your screen, please.
Okay, my colleague, my co-author, Dilara will start.
Yes, sure.
Here also another co-author, Alexander Pak, also is present.
Okay.
Greeting colleagues, can you see my screen?
Yes, we can see your screen well. Just a minute more. Let's wait a minute more.
Okay.
Well, I think you can start. So the first talk is about extractive summary coherence enhancement.
Yes. Greeting colleagues, my name is Akhmetova Dilara, and I'm here to present our work on the Smooth It Up Extractive Summary Coherence Enhancement. So work in developing methods for increasing coherence of texts obtained by automatic summarization is very relevant due to the exponential growth of information in general and scientific knowledge in particular. But the main problem of extractive summarization is selecting salient sentences without any change from the source text. Thus, obtained summaries have a low level of coherence and could be more challenging to understand. So the main objective of this work is an increasing coherence of summaries obtained by extractive summarization method. It means that the readability and understanding the text will be improved. And here is contribution to scientific knowledge. First, we applied large language model fine-tuning approach to solve a specialized problem of increasing coherence level in summaries obtained by extractive summarization method. And also we developed a method for determining the coherence of the text. And let's talk about cohesion and coherence and difference between them. So cohesion and coherence are two important concepts related to the clarity and organization of written or spoken language. Cohesion refers to how well the different parts of a text are connected to each other. It focuses on the relationships between words, phrases, and sentences within a text, like appropriate transition words, pronouns, and repeated key terms that link ideas together. And coherence, on the other hand, is about the overall logical and understandable structure of a text. And it is concerned with how well the ideas and information are presented in a way that makes sense to the reader. A coherent text is easy to follow and comprehend. In simpler terms, cohesion deals with the connections between individual words and sentences, while coherence deals with the overall clarity and logic of the text. And about our data, in our experiment, we used a data set containing 16,772 pairs of extractive and corresponding abstractive summaries of scientific papers in English language. This data set was obtained during the course of work of determining the possible upper boundaries of extractive summary quality, which was published in the article Reaching for Upper-Bound Rouge Score of Extractive Summarization Method by Iskander Akhmetov, Alexander Gelbuch, and Rustam Musabayev. This dataset contains abstracts of length of 1,800 characters on average and extractive summaries 1,900 characters on average, and maximum amount of characters in both types of summaries was around 4,000 characters. And we tried several approaches. First one is a multi-class classification approach, which was failed due to the overfitting, and this approach gives suboptimal results. And fighting overfitting requires large memory capacities. Second approach was sequence-to-sequence approach, which was failed too, and yielded no practical results according to these reasons, like character-based approach works for very small text as phrases or single sentences, but fails for larger text. And beside that, word-based approach requires more than 81 gigabyte memories on GPU and ended with memory exhaustion error, unfortunately. And then we tried a large language model fine-tuning approach, which means that pre-trained large language models are trained with additional data to apply it for specific use case scenarios. We chose a GPT-2 large language model to fine-tune for our text coherence enhancement task because of its availability and simplicity, as well as for the prominent results it gives. And here our experiment design. First, the dataset was prepared to have the combined length of extractive and abstractive summaries not more than 1,000 tokens. Then we added the input and output text signals, token at the beginning of the extractive summary and token at the beginning of the abstractive summary. Then the text were tokenized and divided into the train and test subsets. Then original pre-trained GPT-2 was fine-tuned. And finally, the fine-tuned GPT-2 model was tested. And here you can see the result of our experiment. The original summary by extract summarization on the left side and our generated summary on the right side. You can compare it. So, and about evaluation, our results were evaluated using coherence metric and semantic similarity metric. Coherence metric, which was based on coefficient of variation approach. So we have used a cosine similarity metrics between every consecutive pairs of sentences in the text. And after obtaining these values, we have calculated the mean of these values and standard deviation. And to assess both mean and standard deviation, we use the coefficient of variation metric, which is the standard deviation divided by the mean. And it gives us the measure of variability of the series of numbers, which means the higher coefficient of variation, the higher is variance of the values. And we need an opposite in our work. We need that similarity scores between the sentences would be stable. So it will be indicates that sentences are coherent between each other. And so we took a reciprocal of the coefficient of variation to assess the coherence of the text. And also we applied text similarity metrics to assess the preservance of the meaning of the produced text according to the reference text and input text, in which we used a cosine similarity metric between vector representation of the text. Besides that, we checked the statistical significance of our result using p-value for the Kolmogorov-Smirnov test and z-test. So we have confirmed the statistical significance of our results. And let's see our results. Beforehand, we have measured the coherence of abstractive and extractive summaries for our dataset by 4 different methods, including our own. And we have found that the extractive summaries have lower coherence than abstractive summaries, and their differences is statistically significant. So in our approaches, the Darmovan in his approach showed similar results to the coefficient of variation approach, 0.82 and 0.8 coherence values for the abstractive and extractive summaries, respectively. Their results are also statistically significant, but conversely, we have opposite results measuring the coherence using the Sheehan approach, 0.47 and 10.92 and 0.53 and 12.22 coherence values using both variants for abstractive and extractive summary, respectively. The differences are also statistically significant. And the reason that the approach shows greater coherence measures for extractive summaries might be that it measures the count of transition words in the sentences, At the same time, the extractive summaries contain the most significant sentences from the text, which happen to contain a high amount of such words naturally. But that does not necessarily mean that the extractive summary sentences are bound to each other in a logical manner. And now, about our experiment results. Fine-tuned GPT-2 produced summaries which were much more cohesive than the input extractive summary. It is seen on the table. Input summaries were 3.7 on coherence metric, and predict summaries were 4.28, as the reference summaries were 4.49 on average. So we have increased the coherence of the obtained summaries to a great degree. Predict texts generated by the GPT-2 model without fine-tuning are incomprehensible and very short, so no coherence measure could be calculated. Then we have measured similarity to test whether the new summaries preserve the semantic meaning of the input summaries. So input to reference similarity was 0.81, which is pretty high similarity score, and input to predict by the fine-tuned GPT-2 was 0.79, which is pretty close to the original input to reference or reference to predict. And original GPT produced none of that, so it produced summaries which were not similar at all to the input or reference summaries. And the reference to predict of the original GPT-2 was just 0.08, and the fine-tuned GPT-2 produced summaries which were much closer, 0.8 similarity score. So we made a conclusion that the extractive summary was smooth with large language model fine-tuning approach. And we observed the increase in coherence measure in the generated text relative to the input text, and extractive methods still have potential for development. Thank you for attention. And if you have any questions, me and my colleagues will be happy to answer.
Yes, thank you very much, Dilara, for your presentation. Now we have time for questions. Who would like to ask a question? Please raise your hand. Well, I have some doubts. So you were working finally with abstractive and extractive summaries?
Yes, we were working with extractive summaries to make them more abstractive or coherent.
But these were manually prepared summaries, right?
No. The extractive summaries were obtained during our previous work on reaching the higher upper bound of the extractive summary Rouge score. And the reference summaries were just abstracts from the original articles. Also abstracts.
Okay. So you try, well, so extractive summaries are automatic, and you try to make them better to look like more abstractive summaries.
Yes.
Okay. And how do you fine-tune the large language model?
We take the pre-trained model and make consecutive inputs of extractive and abstractive summaries, marking the difference by the input tokens like E colon and A colon. And then this way we teach the model how should the extractive summary correspond to the abstractive summary. And then we suppose that the language model already knows something, knows in the brackets something about the syntaxes and how coherent text should be built, and we show him or it the clear examples of it. And there were 17,000 examples of it. And after that, we checked on a test set and get some good results, as Dilara showed.
Well, yes. Yes, and well, do you think it can be improved more, or what will happen? Or you have
Yes,
the
we still think that we could apply some different approaches. You heard that we failed on the sequence-to-sequence approach, and we got some thoughts on how to work around the problems with the memory and other things, and obtain some good results. Also, we want to try something with the newer language models like GPT-3 or some open source models like Llama or Stable LM.
Okay, great. So, well, does anyone have more questions? Okay, so if no, then thank you very much. We pass to the next talk, which will be given by Kostuk. So please share your screen.
Yes, 1 second. Can you hear me okay?
Yes.
Okay, good. Now you should be able to see the screen. Can you see it?
Yes, we see the screen.
Okay, very well. So let's start. My name is Ivan Kostuk, and today I'm going to present our work, which is named Automatic Translation of Hate Speech to Non-Hate Speech in Social Media. So in this paper, we presented a data set, a novel task of translation, and some baselines to compare with. Before we start, a little disclaimer. As we are working with hate speech, this work includes examples of hate speech, which may include offensive language and discriminatory content. These examples are used for research purposes only and do not reflect the views or beliefs of the authors. And now let's start. So basically, what is hate speech? Hate speech is defined as a speech or writing that aims to offend a person or group of people on the grounds of race, religious beliefs, sexual orientation, and many other characteristics. With the rise of social media, this problem only increased because now people can hide behind the anonymity in the social medias and do not fear any consequences or any, let's say, basically any consequences for their actions or for their words. Some researchers in the psychology field may also say that hate speech may cause both immediate and long-term harm to the victims of it. As I was saying, it was pretty easy to talk bad on social media. However, when it comes to heated discussions or arguments or many other different debates, sometimes person is carried away and basically says something that some point or some argument in a way that shouldn't be said, but still the argument should be retrieved. And it brings us to basically a task of hate speech translation. The task itself consists of basically two parts. First one being removing hate from the text and rewriting it in a way that the sense or the semantics of the point or of the sentence that is written will be kept, but will be rewritten in a way that it will not cause any harm or will not cause any offensive stuff to the person who's reading it. Because again, we can't fight hate speech. We are trying, but it's very difficult. So instead of fighting it, we suggest rewriting it so the conversations or the arguments still should be kept, but in a better manner and with easier understanding for all of the sides. Here's a little example how it works. So in our case, we selected Spanish for the data set that we are going to use. You can see the English translation below the boxes. I use Google Translate for that, so it's not ideal, but you can get the idea. And basically, the idea is to have the text, put it into the black box of an algorithm that will rewrite it in a much better way with keeping the overall sense or semantics of the sentence that person is trying to say. So why it's important, why it could help the world? First of all, it will help people to communicate more properly, that everybody feels safe and feels welcome, and in general, do not fear talking or commenting anything. Second one is to making this communication much more effective, because when we are not using our emotions in the arguments or debates, we can more clearly talk about our points, different points of views. We can debate in a much better way. So basically, it increases the effectiveness of the conversations. And finally, it's a challenging task in NLP, which also, from academic perspective, is very interesting. It's not that easy to translate hate speech into non-hate speech, and it requires some imagination and fantasy, I guess. So let's talk about the data set, because it's actually one of the main contributions of this paper. We manually labeled the Spanish hate speech data set from Ibarreval 2018 conference. We took this data set, we selected only hateful sentences or hateful comments, so we do not consider anything else. And we asked our people who help us label the data set to produce at least three different translations to the hate speech comment, with keeping the sense, but removing the hate from the text. So basically how it would work, here is an example from our dataset. Basically, you have a hate speech sample, again, with translation in English on the bottom. And the person should write at least three, maybe more, if a person feeling generous, different variation of this particular text without hate speech, but with the same text inside. Sometimes there is a very difficult to understand balance between being aggressive and being offensive. So some of those samples still would be not that pleasant to read, but they will not be hate speech. So there is like one downside of that. So here are the statistics of a data set. Basically, the red line shows the total number of samples, total number of samples that are produced for the total number of samples that were generated with this number of translations. So for instance, as we can see, as we asked our labelers to generate at least three translations, we see that majority of sentences that we have were produced with specifically three variants of translations. So one sentence has three or more translations. Then we have a little bit of 4 and a little bit of 5 and 6 translations as well. Talking about numbers, the total number of sentences, hate speech sentences that we have is 1,608. Total number of translations that we obtained is 5,208. And average translation per text is 3.1, and median is 3.0, which we actually asked them to make. So that's expected. As we don't have really big data set, because it's very challenging and time-consuming to create such a data set, we selected cross-fold validation evaluation strategy, and basically we split our dataset into 4 different folds with the following statistics. As you can see, we split it folds based on the text, but not on the translation. So what it means, if we have a hate speech sentence, which has all of the variants of non-hate speech translations to it, if this hate speech sentence is in train fold, all of its translations as a target will be in the train fold as well, and vice versa. So basically, that's how we split it. We obtained pretty uniform split over the data set, as you can see, and it actually will help us to evaluate our baselines much better. So for our baselines, we selected 4 main models, 4 most common, I guess, models. First one being the classical RNN sequence-to-sequence model, and 3 more were fine-tuned versions of T5-Small, MBART, and Marian models. Marian model is a model provided by Helsinki NLP group, which includes a lot of different which actually has a lot of different models for different languages. In our case, we selected Spanish version of it because we are working with Spanish, and basically we are translating in a way from Spanish to Spanish, but with some semantical modifications. For our metric, we selected blue scores from NLTK package, and we average them over the our false results. The results are not that great because the task can challenge it, but as a baselines, they're good enough. So in our case, MBART worked much better than all other models. So which is not really that surprising because MBART is a model specifically built for machine translation. So it's good. It's good to know. The second place, in a way, takes the Marian model, again, specifically built for machine translation, but with probably less understanding of semantics than MBART. And T5RNN didn't show that great of results because, well, that happens. We also checked the variance, and as you can see, the most consistent results were obtained by the RNN. Well, consistently poor, but well, consistent enough. And others doesn't show that big of a variation between the blue scores. So basically in this work, we provided a new task, we provided an old data set, and we provided some baseline results to compare with. Thank you very much. If you have any questions, please go ahead.
Okay, thank you very much, Yevhen. So does anyone have questions? Well, I have, yes, Tadesse have a question, yes. Go ahead.
Yes, can you hear me now?
Yes.
Okay, thank you very much. Thank you, presenter, for your nice work and for your nice presentation. Based on your presentation, I heard that each head sentence has 3 and more versions. That means non-hit versions. So how do you train your model and how do you evaluate? Because each sentence has another non-hit 3 and more versions. So how do you train your model and how you are evaluate your model?
Okay, well, thank you. So about the evaluation, the blue score itself, it takes as an input basically a text prediction of the text, translated version of it, and the list of different variants of how you can translate it. So in terms of evaluation, that's relatively easy. We just put all of our variants, all of this, for instance, in this case, all of the 3 variants of non-hate speech text and the prediction into the metric, and we obtain the score itself. So in this case, it's, well, easily. About the training, as because it's baselines and we didn't want to spend a lot of time basically building a working method, let's say, because again, this task is challenging and time consuming, but the main contribution of our paper is the data set itself and the task formulation of the task. So we just, extended the data set in a way that for this original hate speech text, we map it to this variant, then we created new sample with, again, this original hate speech text, and we mapped it as a label to the next variant, and so on and so on. So basically, when we have one hate speech text here with 3 possible translations, in our trained data set for translation, we basically have 3 different samples which share the same input, but the output should be different. It's not ideal, but it's, well, it's a start. Hopefully I answered that.
Okay, yes. Well, I have here a doubt. The third manual example says ADEHA, probably it should be YADEHA, because it should start with the capital letter, and without Ya, it doesn't have a sense.
Yeah, probably it's a typo.
Yes. Okay. I have a question. Do you think we can classify the phrases of the original hate speech text according to their intentions? That is, Speech Act classification. So my intention can be here, well, make you stop talking, well, give you an order to stop talking. And maybe it can help generation of the text. Well, I don't know. How do you think?
In some cases, we probably could, but I have doubts about the generality of this approach because it feels like it requires a lot of, well, not a lot, but at least somehow some context to understand what exactly I'm trying to say with this hate comment. We used the Iberval dataset, which was already labeled with hate speech. So it was, if I remember correctly, it was like binary, or we made it binary for us because we didn't care whether it was offensive or hate. For us, it was important that it was something there that should be rewritten. And so the dataset itself didn't provide the context, so we don't know at which point of the debate it was this kind of hate speech comment was made. But some of them, as you were saying, if it's just like shut up, then yeah, we could probably understand that it's an order, and we could provide it to the model as an additional feature. But without the context, I would doubt the generality of such approach.
Well, yes, we shall have a manually marked corpus to be able to use it in the classification, I think, right?
Yep.
According to the Speech Act's theory. Well, maybe later. Okay, great. Does anyone have another question? Yes.
I think Alex has. Yeah.
Alex, go ahead. Alex, we don't hear you.
Yeah, we can't. Maybe
Okay.
you can write it into there is a problem with the mic.
Well, okay, Alex will ask his question later directly to Evhen. Okay. Okay, great. So thank you for your presentation. We pass to the next talk, which is also about hate speech. It is called Audio BERT. It will be presented by, I guess, Mesai Hemeda Yigetsu. Audio means in Spanish hate, so just audio BERT. So it's Bert who is hating someone, I guess. Okay, yes, Mesai, we don't hear you.
Can I start?
Yes, you can start.
Okay, I'm Masai. I'm presenting on the title Audio BERT, or Evaluating Domain Task Impact on Hate Speech Detection. So, as you know, social media and the micro blogging platforms are gaining popularity for fostering connections, yet they pose serious concern. So, the rise of hate speech and the related problem on this platform could escalate into global violence. So this could result in psychological trauma, the reinforcement of extreme belief, or the like self-harm. So the spread of derogatory content or negative stereotype, inciting violence, and foster prejudice against target group. So addressing this issue is the crucial to prevent harm from the consequence. So to address all the above-mentioned problems, various researchers have proposed different approaches in order to detect hate speech, like they use the machine learning, deep learning, pre-trained language models also. So when pre-trained language models offer significant advantage in natural language understanding and generation, so there are also some potential challenges associated with their use, like lack of specificity, computational resource, overfitting of training data. So to mitigate this challenge effectively, it became necessary to fine-tune this pre-trained model on domain-specific data using transfer learning. So in order to that, we built Audio BERT, which is a pre-trained BERT model to address hate speech in Spanish language. In addition to that, we compiled all available datasets, which are available publicly, and evaluated and compared our model or Audio BERT model with existing pre-trained language models. And finally, we studied the impact of domain task and offers advice on how to deal hate speech on Spanish only. So here, as you see, recently, different researchers have achieved promising results by using domain-specific models. So we reviewed on three subtopic research of which a model which focus on a specific language, also focus on a specific task, and related with hate speech detection. So when we see the specific language models, we reviewed about Robertio and Betio, which are trained on massive Spanish text only, and Albert and Marbert models, which are designed to detect or build a model with Arabic language only. So the third language is Bangalabert, which is trained with Bengali language. And when we see the research which then focus on specific tasks is FineBert, BioBert, and LegalBert. When we see to fill the gap of financial statement related thing, we use the FineBert and also BioBert, which are related to biomedical languages. And the third one is LegalBert, which is related with legal unique terminology. So when we come to the research which focus on the hate speech, we reviewed abusive examiner. These models are studying or designed to detect abusive languages in 15 Indian languages. And the third one is COVID hate word, which to identify or distinguish the abusive and the hate speech regarding with COVID-19. So when we come to our data set, we used or we obtained the following data set: Spanish Misocorpus, multilingual hate speech from Kaggle, Homomex, Ascova, Ethernet, and Hetival datasets, and totally we gathered 36,000, more than 36,000. So after pre-processing, we observe around 34,000. We get the 34,000, above 34,000 samples. So there is some duplicated data. So we remove this duplicated data around 2,000. Then when we come to the proposed framework of Spanish hate speech detection, here, as you see, first of all, we use the BERT pre-trained model, BERT. Then we fine-tune with the domain-specific data, which is trained with only Spanish hate speech data set. Then finally, evaluate this fine-tuned model by test data. Then we get the predictive model, which is AudioBERT. Finally, we compared different models from monolingual, from multilingual, as well as from Spanish-centric models also. So then fine-tune this all data with only Hetival dataset by using Hetival dataset. Then finally, we get the result. So as you see here, the experimental result, our model constantly outperformed the spectrum of all pre-trained models, and the outcome of our experiment, monolingual experiment, which indicates that the BERT model surpasses multilingual models. And our finding revealed that model is tailored for the Spanish language, demonstrates a superior performance compared to MBERT and XLMR, as well as also BERT models. So, which this enhanced the capability is attributed to their adaptiveness for grasping this linguistic structure of the Spanish language, the stemming from their pre-training and fine-tuning using substantial Spanish corpus. So conversely, when you see the multilingual model, which encompasses Spanish also, but activated suboptimal performance in hate speech detection when we compare with other existing models. So when you come to the conclusion, these domain-specific models, which fine-tune on domain-specific data, which allow to achieve a higher accuracy based on the performance when compared with the other models which built in for generic models. And when we use this domain-specific model, which requires less training data, also computational resources, also times. It takes less times which compare with the generic model. So according to this, we built audio BERT and which outperformed the existing models. So this is all about our research. If you have questions, you can.
Thank you, Mesai, for your presentation. So now we have time for questions. Does anyone have a question? Yes, Olumide, go ahead.
Good morning, everyone. Thank you for the opportunity. Hello, Mesai.
Yes.
Yeah, how are you doing?
Everything
Can
is
you
good.
go back to the front page, first page?
Okay. This one? Or
Okay. Where did you bring audio out from? What is the audio? What is the meaning of that audio?
okay. Audio means in Spanish is head. So which is head BERT.
Oh, okay. At the same time, as part of contribution, we have all been working on a speech data set. So I'd like to suggest to you, probably if you can compile data set on love so that we can understand how to love ourselves more. I hope you understand what I'm saying. Meanwhile, some of these models you use have been, they have been trained on Spanish. So for me, I think the results are questionable. Like they should do better than what you reported. I don't know if you understand what I'm saying.
I beg your pardon. Just
Okay, go to your results. Go to your result. I said some of the models you used here were trained on Spanish data set. So we expect better metrics than what you reported. I don't know if probably you should look into it again. These are pre-trained language models. So they have reported very outstanding results in earlier research than what you reported. So I'm guessing if we look into this again, probably these results can be better.
Okay.
So that's just my suggestion.
Okay.
And don't forget, I'll be hoping that you work on love speech data set. Thank you.
Okay. Thank you.
Okay, thank you, Olumide. More questions? Okay, I have a question, Mesai. If we will train MBERT, fine-tune MBERT, if we will fine-tune MBERT, which is multilingual BERT, and it contains some data for Spanish already, do you expect the results will be better, worse? What will happen?
Actually, when we took this data, or when you select the multilingual data to assess how well the multilingual models perform in the downstream tasks, but it also we obtain the Spanish language in this multilingual, but I think there is some problem because it takes a long time to train. Also, there is some struggle to identify some specific or unique terminology in Spanish. That's why. So I think it doesn't perform well when you compare with domain task.
Well, okay. Well, probably it would be interesting to check this situation with the various types of BERT. So if you are fine-tuning the BERT, well, if you will fine tune the other birds, what will
maybe I'm planning to train or fine tune the model which you like Beto or Roberto, because which are designed or trained only on massive Spanish text or corpus only. So I think maybe I will get better when we using this Beto or Roberto model.
Okay. Okay, great. More questions? No? Okay. If not, then thank you, Mr. for this presentation, and you have the next presentation as well, right?
Yeah.
So it is also about hate speech, but with a specific target audience of the hate speech.
Okay. So can you start?
Yes, please.
Okay.
But we don't see your screen.
Oh, okay. Let me stop this one. Okay. What about now?
Yes, we see it.
Okay, so now I'll present on detecting multilingual hate speech targeting immigrants and women on Twitter data. So the spreading of this hate speech or the aim to immigrant and women on social media platform is just troubling issue. So this includes the dissemination of offensive, discriminatory materials, contributing of the reinforcement and provoking violence also. So here there is the consequence of hate speech dissemination over immigrants and women on these social media platforms, which include like psychologically, which affects on its target, which leading to increased stress, anxiety, depression, and like feeling of like isolation. And this hate speech, which leading to social exclusion and marginalization of migrant communities and women. And it can create like barriers to their integration into society and hinder their access to equal opportunity and resources also. So this hate speech can escalate into the real world acts of discrimination and harassment and also violence. So these research are as different contribution among those. Here I've mentioned some of them. So the first one is we try to improve the result when we detect this task, hate speech, and also try to identify abusive and also target range. So at that time, by using the balancing technique, we try to improve our result or performance of the model. And the other one is we make comparative analysis based on deep learning approaches and our proposed approach. And finally, we emphasize the significance of constructing the equivalent monolingual and multilingual hate speech models. So before I'm going to the data section, I have to say one thing. When we are using the detecting hate speech by using different models, the result or the performance bias to one classes with a class which that has like more or majority of data. So the result will bias. So in order to mitigate or to address this bias, we used different data balancing techniques. So there are a lot of data balancing techniques. Among those, we used the random oversampling and undersampling methods. So here as you see, our data is collected from publicly is available from HETival dataset. So the entire dataset are around 19,600. Among those, 13,000 are from English tutor, and the other rest of 6,600 tutors in Spanish. So here, as you see, the statistics of dataset of each language. When you see the Spanish, you can see unbalanced and balanced data in two techniques also. You can see here. So we classify each language dataset in three classes: hate speech, target range, and aggressive behaviors also. So when you see the hate speech, there are two classes: hate and not hate. In target range also, it's individual and group. In third one is the aggressive behavior, also aggressive and not aggressive. So we use this dataset from HETival. So when you see here the hate, for instance, we can see the hate speech dataset, there is unbalancing here. So the hate speech are 2,739. So when you see the not hate is around 3,861. So if we build a model to identify or to detect this hate and not hate, the model or the performance will bias to the not hate class because it has more data or samples here. So in order to address this problem, we used two techniques: undersampling and random oversampling techniques. So when you see our architectures, we aim to address this challenging task by detecting this hate speech, aggressive behaviors, when also performing target classification. So to tackle this, we explore and propose several deep learning approaches like LSTM, BioLSTM, SaneMain, and also JARIO. So these all are classifier. So when you see this architecture, we can tell something about this. Each of these models offers the unique capability in understanding and capturing different aspects of input data. So to ensure through this evaluation, we conduct experiment using each of these models individually for mentioned tasks. So we analyze their performance and compare the results obtained from each models. Then when each model shows promising results individually, but we observe that there is no single models constantly outperform the other across all tasks. So based on this finding, we use or propose this ensemble approach by combining the top three performing models so that we benefit from diverse strengths of each individual models. So we employed the boosting in ensemble model, which works by iteratively training a weak learner or base model and combining their prediction to create strong predictive models. So here, as you see the result in all results, we build model and we try to detect or identify these three tasks: hate speech, aggressive behaviors, and also target ranges. So in all, our proposed model outperformed. So when we come to the conclusion, we consider both monolingual and multilingual data sets and just like imbalance through random undersampling and oversampling technique. And these experiments are perform for each dataset, and effectiveness of their balancing techniques also using by unbalanced, which our ensemble deep learning approach provides improved accuracy in order to address this task. And finally, we use when you see or observe the above experimental result using this under oversampling techniques generally lead the high performance or achieving high performance when we the dataset exhibits there is less amount of differences in the size. So this is all about the research.
Okay, thank you, Misai. So we have time for a couple of questions. So does anyone want to make a question? Well, if not, okay. Well, I have a question. When you say undersampling, you mean you just remove some objects, right?
Yeah. When we use the undersampling, that means we remove instances from the majority class, but there is also some disadvantage when we use this thing. Maybe we may lose potential information from dataset. So in order to that also, we are planning to add, there is a lot of techniques. So to improve that thing, we try to use other balancing techniques.
Yes, and then you say you use oversampling.
Oversampling, yeah. When
You
we
just
use
replicate your objects, or you do
duplicate,
something
yeah.
else?
We duplicate the dataset in minor section class. So at that time also we faced some problem. It's for most of time when we predict the models, there is happen like overfitting is happened. So due to that, we are planning to use a different type of balancing techniques also.
Okay. And you mentioned you have 3 classifiers.
Yeah. No, basically, we are using around 4 deep learning approaches: LSTM, BLSTM, CNN, and GRU. Among those, when we use the ensembled approach, we combine the top 3 models. By using top 3 models, we let me show here in the architecture. For instance,
I understand that that you are using 3 classifiers, but what are these classifiers?
We didn't decide at this time, but when we training the model, for example, we used totally for deep learning approach, LSTM, BLSTM, CNN, and GRU. Among those, we combined the top 3 only.
Okay. Well, okay, great. More questions? Well, if no, then thank you, Misai. Now we have presentations of Olumide. Please share your screen, Olumide.
Thank you, sir.
Yes, your screen.
Yeah, I'm trying to. Can you all see?
Yes, we see. Thank you.
Okay, thank you. So the title of my presentation today says Med AI Dialogue Corpus, zero-shot classification of doctor and AI responses in health consultations. Statement of the problem. a critical problem has emerged in the health sector. We have seen in recent times the pandemic, new diseases, symptoms from people. We are now reporting symptoms based on lifestyle changes, the type of food people consume. So making the hospitals and overwhelming the healthcare professionals. So as a result, different healthcare platforms, different healthcare groups have resulted to creating different platforms to attend to patients online. So what they do, they collect, they ask questions, they respond to those questions, and then they provide answers to patients. We found out that some of these platforms claim to have doctors in real life, whereas they have integrated AI models into their systems. So they just use that opportunity to respond to people. And we know that symptoms reported by patients, they are not to be attended to by AI models, because sometimes if you report, if a human being, a doctor can feel emotion in text, models may not be able to understand what you are going through and may not be able to provide adequate answers. So we decided to collect text from AI systems and real doctors' responses to patient questions. And then we decided to prepare them for different NLP tasks. So we found that there are few corpora for doctor AI consultations that understand new unforeseen medical conditions. Of course, we know this is the era of large language models. And so we expect that this is a new avenue to conduct research into text generated by models. So this problem is not only technical, but also extends to ethical considerations, because we know that humans may not want to reveal what they are going through. And so models have a way of saving your details and making it available to the public. So apart from trying to understand who is responding to the questions that patients are asking, we also want to ensure that these questions and these symptoms reviewed by these patients are not revealed online to the public, especially if the patient did not authorize them. So to identify the gap in this existing corpora, we propose the MEDIC corpus that we use for this classification task. We know that medical knowledge is continually evolving and new medical conditions are emerging. So therefore, we understand we understand that it is important to create this corpus, and because it is relevant to this present age, because we know some years ago we don't have COVID-19, for example, but now we have COVID-19, and we have questions relating to COVID-19 and some other new diseases that have evolved. And at the same time, we are creating zero and few shot learning systems to make accurate predictions with these examples that we have, because we know that we can never have it all. Medical conditions will keep on coming out. There are some questions some AI models can answer now that they won't be able to answer in the future, because the medical conditions are new. So we cannot accurately certify supervised learning, that is not zero or few shot, because we know that this learning does not include all medical conditions that we have seen, since they are still evolving. So these are the statements of the problems and the objectives of this research. So the implications of this study is that we were able to contribute to progress in AI-assisted healthcare by enhancing clarity between healthcare professionals and AI systems. So with our systems, we can, if it is deployed, patients will be able to know if the response to their questions emanate from AI models or from humans. And that with the development of this corpus, we have more information about unknown medical conditions. And the development of this high quality data set in healthcare AI impacts not only classification tasks, but we can also use it for other machine learning applications. And our studies have implications for the education and training of healthcare professionals, and this corpus serves as a foundation for ongoing work in the development of classification models. The abstract of our work: we know that zero-shot classification models are supervised models. They have been trained on existing data sets, including in the healthcare domain. But like I've said earlier, they have not seen it all because the healthcare sector is continually evolving. So in this research, we try to investigate the effectiveness of these retrained language models to accurately classify these doctor AI consultations, without specific learning through zero-shot. So we aim to determine whether these models can effectively detect the origin of this text, if it is from human or from AI models. And in order to perform this research, we collected responses from doctors to patient inquiries about their health. And then we posed the same questions to models. We asked ChatGPT the same question. And then we also rephrased the doctor's response. So that's what I mean by we pose the same question and response to AI models. So we have two versions of AI-generated text. So while zero-shot language models show good understanding of the language they are trained on in general, we observe that they have limitations in classifying this particular type of healthcare text. And the reason is well understood, because we know that they might not have seen some of these newer medical conditions. And this research lays the groundwork for further research into this field of medical text classification, informing the development of more effective approaches to accurately classify doctor-generated and AI-generated text in health consultations. So to introduce, we know healthcare is an integral part of our lives. All of us, we have something to do with healthcare at one point or the other. If we are sick, we may not be sick. It could be our close or loved ones, or family members. It could be when we are trying to give birth. We all know healthcare is an integral part of our lives. So maintaining, promoting, and restoring health is important. Now, these days, we know there is rapid advancement in AI, and these advancements have been integrated in medical consultations. So we're using NLP tools to understand, to analyze, and classify text authored by doctors and AI models in medical interactions. It's an important part of this field. So we have proposed zero-shot in this task as a widely accepted approach in various NLP tasks that lack sufficient training data. So we know this particular task will never have sufficient training data, because we will continue to have newer diseases, newer models, newer pandemic, and we are expected to prepare for them. And that's why we are trying to see if we can adapt some of these models to the challenges that will come up in the future. So the question here is that as AI-generated responses in the medical field are constantly evolving, will zero-shot classification be a solution that leverages transfer learning to solve the problem of detecting doctor and AI-generated text in health conversations? So we divided our task into 3. Our first task is to be able to classify ChatGPT-generated text and text provided by doctors. The second task involves differentiating between text rephrased by an AI model from the doctor's response. The third task involves classifying the combination of these first 2 tasks as a multi-label task. So in this third task, we have ChatGPT generated responses, which is an AI generated response. We have rephrased responses from doctor's text, which is an AI generated response. Those rephrased texts, they just pick some important keyword in the doctor's text, and then they wrote something new about those keywords. And then we have the last one, which is the original doctor's text, which was written by human. So we created this corpus by visiting this website, questiondoctors.com. It's an online platform that provides patients with free medical advice for answers to health-related questions from the comfort of their homes without prior appointment. We know that the pandemic, different diseases have overwhelmed the health sector. There are not enough doctors, there are not enough nurses to attend to people. So there is a rise in people turning to online platforms for solutions to their health needs. So this platform is one that is equipped with verified doctors. They have been verified, and they have a submission process that is straightforward and requires users to provide relevant details about their concern, such as symptoms, medical history, and any additional information that can help diagnose their problems. So with this information as human, you can connect the dots and provide adequate medical advice to patients, which AI models may not be able to do. Once a question is submitted, they provide responses to users within a specific time. It could be within 24 hours, depending on the availability of a specified professional. So it depends on on the need of the patient. You could get answers fast, and with that, you can progress with the management of your symptoms. So this is a verified website. We have so many other ones that are out there that claim to have verified doctors, but they are not true. They provide answers with AI models. So, which is why we are trying to detect if the source of text patients received are from medical professionals or from AI models. So
sorry, you have about 12 minutes for the whole presentation. So
okay.
Just few minutes left for you, please.
Okay. So the data set was rephrased using this Rapid AI website. They gave us an API that we use to rephrase the website, the data set, and the snippet of the code we used for the paraphrasing is shown. The statistics of the data set is shown. We have the DC data set is the doctors and the ChatGPT's response. We have the doctors and the rephrased text response. Then the DCR is the doctors, ChatGPT, and the rephrased text response. So each of them contains 3,716 instances, which means we collected half of these as questions, and then the answers by the doctors and the ChatGPT combined gave this and this and this. So we sample questions from the website is shown. We have questions and the answers. Then sample questions provided by ChatGPT is shown. We have the same question and the answers provided by ChatGPT. And then sample responses rephrased by the AI model is shown. So we have the question and the rephrased response. So we have 1880 distinct text instance for each of the questions and the responses we have. So we were able to show some features of the data set. We found out the most common words for the data set, and for the doctors and the ChatGPT's response. We observed that despite the fact that ChatGPT is trying to help, it is always referring people to still consult a doctor, a medical professional. So if you see here, you see that most common words in ChatGPT response included healthcare professional, medical. So it is still saying, despite whatever I say, I'm not sure of it. Consult, you see consult here. So we see in the most commonly used words in the ChatGPT's response that is still referring people to consult healthcare professional and not rely solely on them. And then we were able to show the unique words per label. We found out that these AI models generated unique words, probably different from what the doctors used. Probably they just look for synonym, which may not be accurate. And then the same thing with the number of words. We observed that generally ChatGPT or these AI models used more words to respond, despite the fact that we posed, we told the models not to give more than a specific number of characters, which was 250. But we observed that generally they were giving more characters. They were maintaining that 250 generally for most of their responses. They couldn't give short answers. So we have the unique words for the responses, and they are shown. So like I said earlier, we have observed that there are more unique words in the AI models. And then this is the distribution of the text length. So the maximum number of characters is about 250. And then our analysis shows that we can zero-shot classification models achieve precise classification results for data from classes unseen in the training phase. The models we use are BAT, and XLM, cross-lingual language model. We use this. All these are zero-shot versions of these models that we use for this particular task. The results are reported, which shows that these models struggle to classify this text because they have not seen some of them before. So they struggle to classify them. This is for the first data set, the doctors and ChatGPT data set. This is for the second data set, doctor and rephrase doctors data set. They struggle to classify them. This is the third data set, the GCR data set. We found out that the model couldn't distinguish between these three data sets. And the results of the metrics are very poor. I mean, the classification reports are very poor. So this research was just, we did this as a baseline into trying to classify text, because we know that these texts are not what we are going to have completely. So we cannot use supervised training, because we know that we will continue to have new medical conditions. So if we are trying to develop models that can be useful both now and in the future, we decided to use zero-shot as a baseline model for this task, where we classify these doctor and AI generated responses in health consultations without corpus training. The result of our study demonstrate the strength and the limitations of the various zero-shot classification models. And despite the challenges encountered, the potential of transfer learning and zero-shot classification remains promising. And then we are hoping that with further fine-tuning and specific corpus training in future tasks, these models can improve their performance in this classification task. And these are our contributions. We created this data set comprising responses from this. We have been able to answer the statement of the problem, the research question. So we're able to show the patterns, the distribution, the relationship in the data for researchers and analysts. We have been able to show that ChatGPT or AI models cannot provide answers. They still refer people to medical doctors. So it is important that patients are sure of where they are receiving answers from when they seek solutions online. So we also explore pre-trained models for zero-shot classification, and we analyze this. Thank you. Any question?
Great, thank you, Olumide. Does anyone have questions? Yes, it is certainly a very interesting problem, I think, and well, the corpus is quite valuable resource. Well, the results is about what 53% in binary classification.
Yes.
Yeah, in binary classification. 58.
Yes. This is for the first binary. This is for the second binary. And this is for the three-label data set.
Okay, but the classes are imbalanced, right?
No, they are balanced, of course.
Balanced.
It's just question and answer. So the same questions from the same responses from the doctor, the same responses from the model, the same responses from the other model. So they are balanced.
Yeah, but okay, yes. Yeah, but these results show that yes, it is very difficult to distinguish the human and the bird results.
Yes, based on this analysis, and the reasons are well understood. Just like we said, despite the fact that these models understand English, they have been trained on English, but medical conditions are evolving. They have not seen some medical conditions, and we have seen from what we have experimented that because medical conditions are continually evolving, it's difficult for these zero-shot models to provide answers.
Okay, great.
From doctors.
Okay. Yes. Misai has a question. Yes, go ahead.
Okay.
Okay. Thank you, Olu.
Yes. Welcome.
I have some questions. What are the key challenges and the consideration when implementing this zero-shot classification approaching?
We didn't use any specific feature in this task, just the transformer embedding for their respective models.
Okay. But when you are using I think the data set is from medical data set. So how do you consider about the privacy of the patient?
Okay, I did not show the username of the information of those who reported those questions. It was not reviewed, of course. So their privacy have been hidden. So we just showed this question and the response. So, and we also emphasize that it is important for the patients to be sure of where they are asking questions from, because some of these AI models, ChatGPT updated their policy recently that whatever question you ask them, they're going to reveal it to the public, So if patients are aware of the systems that they are asking questions from, and they can be sure that their privacy will not be revealed to the public. So for us, we didn't review the users, just the questions and the response that we use. Even the privacy of the doctor is hidden. I mean, it's not reviewed. We didn't say which doctor responded, even though we have those information.
Okay, so as my first presentation, I would like to recommend something, because this medical is one of domain which has a unique terminology and the vocabularies. So it would be better to develop a domain-specific model, I think. So I recommend that.
Okay, thank you so much. And of course, you know, there are so many machine, like I said earlier, there are so many machine tasks, machine classification tasks that can be done with this model. My next presentation, I use another specific approach to tackle the same problem. And I have some other upcoming work that have decided to use another approach. So it's a data set that can be done with different methods, you know, that it's something we can apply different methods just to continue to improve this classification task.
Yeah, thank you.
Okay, thank you so much.
Okay. Thank you, Ms. I think Olumide, we have other question in chat by Jesus Miguel Garcia. Which are the classes in multi-class?
Which are the classes in multi-class?
Yes.
Okay. The classes is first the doctor's response. So we label that as probably 0. The second is the ChatGPT's response, labeled as 1. The third one is the rephrased response by this rapid API that was shown earlier. So those are the 3 classes. So the classes here in the first DC dataset is doctor and ChatGPT. So those are the 2 texts we're trying to distinguish. The second one is doctor and rapid API. We are trying to distinguish. The third one is doctor, ChatGPT, and rapid API that we are trying to distinguish. Did I answer your question?
Yes, I think that yes.
Okay.
Okay, great. Thank you, Olumide. Now we pass to the next presentation of Olumide.
Okay.
Yes, please. Remember, you have just 12, 13 minutes.
Okay, thank you. So this question, the next one is enhancing clinical discourse, evaluating embeddings for one-shot classification of doctor AI consultation. So in this scenario, we decided to perform one-shot classification, knowing fully well that we may not have enough data sets in the future, but what if we are able to show few data sets to these models, if they will be able to perform well with this classification task? In the first paper I presented, we couldn't use traditional machine learning because we know that they are not zero shot. They cannot learn without seeing any training data. But in this task, we decided to incorporate traditional machine learning models, algorithms, for this particular task. So we know that there is an absence of models showing different performance of embeddings in one-shot classification of text generated by doctors and AI models. So in order to identify these most effective embedding techniques, I will not say we know, I have searched. There are other classifications, performance of embeddings in different tasks, but for this particular doctor-generated and AI-generated text, there are no or very few, which is not even specific to patient inquiries, performance of these embeddings. So in order to identify the most effective embedding techniques to evaluate and compare these one-shot classification systems, we decided to embark on this task, and we use traditional machine learning algorithms. So the problem at hand is not only technical, like we have said, you know, we are trying to see if we can also consider the ethical reasons. So we developed several one-shot classification systems for this classification task, using different embeddings as features. So the implications of this study is that the evaluation of these embeddings could lead to development of more accurate and efficient models that can enhance clinical discourse during AI consultations. Effective embeddings can enable the creation of personalized healthcare solutions that can adapt to patient profiles, which will contribute to building trust among healthcare professionals. So since we have been able to improve the classification results we reported earlier, we have a higher percentage of possibility, and patients will be able to know that a text that I receive is from AI professional or from, AI model or from doctor. So it can build trust among these healthcare professionals that is responding to them, or whichever hospital that integrates this platform. At the same time, our findings can provide guidance into choosing the best embedding techniques and machine learning algorithms for one-shot classification tasks, both in healthcare and other domains. So if we are able to report that a particular embedding in combination with a particular algorithm performed well, we can provide guidance for others who are looking to perform this type of tasks in another domain. They could try it out and also report either the same or something better or less, something like that. So the abstract of this work, our results highlight the reliability and adaptability of these embeddings, because the embeddings we reported, we found out that word-to-vec, GLOVE, character engrams, and GPT-2 embeddings, they all demonstrate noteworthy performance, and that this machine learning architecture can be used to improve the quality of healthcare conversations when training data are absent. If we just have an example of a text from a doctor, from ChatGPT, from a model, we can use that one instance of that example to facilitate better communication between patients and healthcare providers. So we develop representations that can capture features of text. We developed these embeddings, which have applications for industries in healthcare, where information exchange is crucial. We were able to identify source of the text, which can allow patients make informed decisions about the medical advice they receive online. And these embeddings are a key component for classification models to be successful. So just like Mr. has suggested earlier, he wasn't aware that I've carried out some of this. So in this task, we decided to see how these representations can help our classification, but in this case, using traditional machine learning algorithms. So like before, like the first paper, the tasks are similar. So we are classifying the DC, DR, and the DCR data set. The corpus is the same, and the data set statistics is the same. So the proposed models includes the logistic regression, the random forest, the support vector machine, the Gaussian bias, the decision tree, gradient boosting, the multi-layer perceptron. So we use this to, we apply these models on the medical corpus, and then using different embeddings. The embeddings we use included the bag of words, character engram, word-to-vec, GLOVE, fast text, and the GPT-2 embedding. And we evaluated their performance based on the accuracy, precision, recall, and the F1. So we report the scores here, and then the scores varies depending on the data set. For this first data set, the DC data set, we see a general improvement across all the embeddings. So we see bag of words doing well here, we see character engrams doing well, we see word-to-vec. Despite only seeing one instance of this text, they were able to perform a better classification than the zero-shot classification. And we move to the random forest. Here, for some of them, the embeddings perform poorly, but we see here the word-to-vec, the GLOVE, the fastest GPT-2, they all try their best. For the support vector, we see an increased performance, except GPT-2. For the naive bias, we see an improved performance. For the decision tree, the performance is reported. For the Gaussian, we see, for the machine multi-layer perceptron, we see the performance. So the best performance was reported somewhere around there. We see another good one with this character engrams here. We see word-to-vec. This is for the DC dataset. So we observed an improved performance in this data set in the accuracy or the F1 scores. For the next data set, which is the doctor's response and the rephrased response, we know that these two texts contain the same keywords or probably similar. So the models struggle to classify them because what the rephrased text did was to pick some keywords in the doctor's response and generate a new text with it. So we expect this type of classification result in this second data set. So we perform, we used all these embeddings as features into all these models and we report the result for this. Then for the third data set, we understand again why this result is like this. But generally, we see occasionally that the character, Word2Vec did well in this case. We see that character engrams did somehow a little bit okay here, and then like that. So we see Word2Vec character engrams making over 50, Word2Vec here making over 50, character engrams Word2Vec glove here, and then like that. So we were able to show the accuracy of these different models in this chart, where we report that these three models consistently try their best. I mean, embeddings, character engrams in most of this. This is for the first DC data set. So we see character engrams, Word2Vec glove being the highest in each of the charts. We see them. Then here we have fast text coming up occasionally, and then fast text coming up. But generally, we see a good performance of character engrams, Word2Vec and glove in the first DC data set. So in the second data set, we see that GPT-2 embeddings, probably because of its language understanding features, we know that it can understand contextual features. So it's able to pick the contextual difference between this DR data set and consistently gave a good result on this second data set. In this third data set, we see the consistent performance of the Word2Vec in most of the models. Then occasionally we see the back of words doing well there. Then generally the multilayer perceptron model did better than others. We were able to show the heat map for these classification scores, the red being the highest. So if you just want to randomly look at how well these models and these embeddings perform, just look at this place. So you see character engrams, Word2Vec glove generally performed by looking at the statistics here in this data set, and then others, their performance were reduced. In this case, we see that the performance were reduced generally, and just the GPT-2 embedding alone showing slight improvements in some with some models. So, and we have explained why it is so. So we see it did well here with the multilayer perceptron, with the decision tree, and the random forest classifier. Then in this third case, we see just some none of the models did exceptionally well. None of the embeddings. We just see right here, we see Word2Vec doing well with logistic regression. Right here, we see character engrams doing well with these two models. Right here, we see bag of words doing well with this one. Right here, we see GPT-2 doing well with this. So we just have each of these models performing well at random and not consistent on the third data set. So this research has investigated the performance of various embedding methods in the context of one-shot classification. Our results reveal variations in the performance of different embedding methods. And so the choice of model and embedding, if anybody is willing to apply, should be customized to the specific data set. Like we have observed that the performance varies depending on the data set. If it is from doctors to newly generated text by AI model, then you can choose a good performing model there. If it is from doctor and rephrased response where the model picked some keyword in the doctor's response and formed a new text with it, then we can pick a good performing model or embedded technique from this second report. And if it is for a multi-label classification where we have text generated from different AI models, we can pick a good embedding or good machine learning algorithm if we are intending to apply from this third result. So we say our result should be customized based, the application, the choice of model and embedding should be customized based on the data set you have. Then this result emphasizes the role of context and data characteristics in determining the optimal model embedding combination. We observed here especially that the GPT-2 embedding were able to understand context better. Of course, we know why. And then, so there's a strong performance of all the embeddings across all models, especially for the first data set. And for the others, they have similar performance, not so different. And then depending on the data set, generally, we found out that word-to-vec, GLOVE, character engrams consistently perform well. We also observed that GPT-2 performed well depending on the data set. We suggest that GPT-2 embedding can be well suited with models developed for this specific one-shot task. And the reason could be because of its understanding capabilities. We suggest that its embedding representations align well with the models. So we were able to advance our earlier study by developing embeddings and knowing how well it impacts the classification of doctoral consultations. We were able to benchmark these AI models, multiple one-shot classification models, eliminating the need for extensive training data. Our analysis involved the classification of these tasks as both binary and multi-class classification. Thank you so much.
Thank you, Olumide. Thank you. Now, do we have questions, please? Is this work the direct continuation of the previous one?
Exactly. Direct continuation. At the same time, in the next task I'm working on, I've started using contextual embeddings with only pre-trained language models as an improvement to this present task. So as a future work. So it's a direct continuation of the previous one.
Okay. So you mentioned GPT-2 embeddings. Well, I'm just not familiar. It is the same like word-to-vec, or is it something different?
No, it's different, of course,
No, I mean the methodology of the construction of these embeddings. Is it similar or is it something?
It is different.
But the idea is the same, that you represent each word by some vector and it is universal.
Exactly.
Because you say that in some tasks it performs good and some tasks not so good.
Yes, just like it is supported. Although we know that for this first case, we should expect that this GPT-2 embedding will do well, but we know these are traditional machine learning algorithms. They are not made for this type of embeddings. So we understand why they performed this poor. So I decided to use GPT-2 embedding as one of the transformer embedding because it is a language generation. It was used for language generation task, and we know that this particular text is also a language generation task, where we are asking models to generate text based on questions we are asking. So thinking the embedding will be able to understand how texts are being generated by AI models. Of course, it does, but probably with these models, these models are unable to understand the vectors presented by these embeddings.
Okay, great. More questions? Okay. If no questions, then thank you, Olumide, for your two presentations. And now we pass to the last presentation of this session, which will be by Carolina Martín del Campo.
Thank you so much.
Carolina, can you please share your screen? Yes.
Yes.
Yes, we see your presentation. Yes, you can start, please.
Well, I'm going to present the topic refinement of word embeddings when segment content using multi-output neural networks. Well, in natural language processing, word representation is essential for many tasks. It exists two basic types of representation. That is one-hot encoding, where each word represents an index of a vocabulary, and vector-based model, also known as embeddings, where each word is represented in an n-dimensional space as a vector of continuous numbers. The embeddings encode similarities between word vectors, capturing lexical and semantic relations, while one-hot encoding does not capture any semantic information. Both representations have been widely used in different tasks of NLP, considering two specific tasks, emotion classification and sentiment analysis tasks, give good results, even considering that neither of these representations carry any emotional information. Recent research related to the two mentioned tasks focus in deep learning models using transformers. This research basically focused in trying to improve these classification tags, trying to inject some emotional information in the pre-trained word vectors. So in the state of the art, there are two basic approaches. The first one is learning sentiment word embedding from scratch, and the second one is refining pre-trained word embeddings. Considering that the second approach has better results in the state of the art, I'm going to talk a little bit about this. In 2018, Agrawal et al. Proposed emotional word embedding. Basically, the author used a multi-class classification using the 6 emotions: anger, surprise, disgust, enjoyment, fear, and sadness. What they did is basically use an LST model with a embedding layer with pre-trained growth embeddings. And well, after the training of this classification task, they extract the embedding matrix and use them as embedding emotional word vectors. They show that they have a better performance than traditional word vectors like love or word to text. Another approach was proposed by Nadal Bohut and Setzer with sentiment-aware word embeddings, where the author used feed-forward network to predict the polarity and a principal component analysis. They used in the same way growth as pre-trained word vectors. Well, once the feed-forward network was trained, they extract the hidden layer of the model and concatenate the values with the original vectors to keep some of the information of the original vectors. So they finally use PCA to obtain the final representation. In 2022, another approach was proposed by Saha et al. To learn a transformation function using a customless function and BAT. BAT is what they call in psychology the 3 basic components of emotion, where balance is the pleasantness of a stimulus, arousal is the intensity of emotion provoked by a stimulus, and dominance is the degree of control by a stimulus. Basically, they use a Euclidean distance between the original vector and the resulting vector after passing through the MLP as loss function. Well, they see this as a linear regression problem, considering that the bad values are values between 2 and 1. And well, finally, they show an improvement with respect to the other approaches. Well, in this work, we're using multi-output networks that basically are used to predict multiple outputs given an input, allowing diverse output data types. So we are trying to simultaneously learn emotional context and polarity context using a combination of lexicons and PCA to obtain the final dimensionality. To this end, 3 lexicons were used. The first one with values of BAT and the other ones with values of polarity. The resulting combination of these lexicons are, this, as we can see in this table, we have around 20,000 words as negative, positive, or neutral, classified, each one with bad values. Well, this is the multi-output network proposed, where in the input layer, we have the globe value of each of these words, and as output, we're trying to make a regression and a classification to obtain the bad value and the plurality of each of the words. For example, for the word terrorism, we insist to the network the global representation of this work and trying to predict simultaneously the balance values are shown here and the polarity values shown here. Well, after making this prediction, having the network learn the representation of each word, we remove the last two layers of the network, and we keep the rest of the network to predict the value of the rest of the words in the globe. So once having these values, we concatenate with the original word vector to try to keep some of the original content of the vector. And finally, we use CCA to reduce the dimensionality. To test these embedding generators, 3 corpus were used. The first one with the 3 labels, positive, negative, and neutral, semi-val. The second one, the Stanford Sentinel Tree Bank, FST2, with 2 possible labels, positive or negative. And finally, the International Survey of Emotion, Antecedents, and Reactions, ICR, with 5 emotions: joy, fear, anger, sadness, and disgust. BLSTM was used to make the classification, and well, these are the results obtained with different approaches. As we can see, our proposal have the best performance for 2 of the 3 tasks, having the best performance for the fine-grained classification. So we can conclude that our proposal network successfully captured the emotion information, given that, well, we have the best results for the fine-grained classification. However, well, an improvement in polarity can still be done, considering that, well, the results, considering the comparison with the state of the art, are practically the same. And well, here are some of the references, and that's all. Thank you.
Thank you, Carolina. Now we have time for some questions. So does anyone want to make a question? And what is this valence, arousal, dominance? What is this?
Sorry?
What is valence, arousal, and dominance? What are these features?
These values are 3 characteristics of, let's say, in psychology, they call 3 basic components of emotions. They say for each emotion that present a human, they are going to have the balance. There is the, let's say, the presence of that emotion, the arousal, the intensity provoked by that emotion, and the dominance, the control that a person have about that emotion.
Okay, great. Thank you. Okay, so other questions? Well, okay. If there is no other questions, then we finish this presentation. Thank you, Carolina. And we had all presentations, so our session is over. Thank you all for participating in this session. Okay. The authors, please don't forget to improve your papers and submit it in the timeline, which will be communicated to you later. Okay. Great. Thank you very much to all of you. Goodbye.